All right, we're going to take a look at lessons 2-3 and 2-4. On your packet, I should have titled it 2-3 and 2-4. I forgot to do so, but this lesson is going to be 2-3 and 2-4. When it comes to Delta Math time, you will only have one lesson. You will not see a 2-3. You will not see a 2-3 lesson in Delta Math. You will only find a 2-4. I've combined them together. 2-3 is a very, very, very short lesson. So I just combined them together, and we're going to try to get through both 2-3 and 2-4 today. So we're dealing with exponential functions. And I don't know if you remember, but last class I gave you this equation. I said, hey, if you're on Delta Math, an exponential function in general form will be shown to you as being f of x equals a times b to the power of x. You might remember that. But I told you, hey, that's kind of weak. And so we changed it for our class. Do you remember what we changed it to? We said y1 first because a lot of people forget what a is. Y1 times base to the power of x minus x1. Yep, we changed it to that to help us out. Now, what we're going to talk about today on lesson 2-3, which is really just the first couple slides, is that this initial value, the y1, the y1 is the initial value. And again, you could put y1 or the letter a, whichever you prefer. I'm going to use y1 because I think it's going to be more helpful for you as we move on through the school year. So that's the initial value. There's some things that have to be true. Y1 cannot be 0. Why would it be a problem if y1 was 0? When you multiply, you'd only be left with 0. So y1 here cannot be 0. And again, you could say y1, or if you desired, you could use the letter a. So y1 or a cannot be 0. Now let's talk about the base. This base must be positive. That's what greater than 0 means. Base must be positive, but it cannot equal 1. If the base itself was 1, 1 to any power. 1 to any power is 1, and then you're just with a constant function, it's not exponential. So based off that, we get these basic graphs, okay? Now, they had the point here, 0, a. Based off the equation I give you, any certain random point, just go ahead and put a point anywhere randomly. It doesn't matter where you do it. Just do x1, y1. The reason I want you to know this formula is it's more powerful. So if they don't give you the y-intercept, if they just give you some random point, you can plug it in and be off and running anyways. Does that make sense? That's why I'm giving you the other formula, so that you can be off and running if you don't get the y-intercept. We talked last time, exponential growth means what's happening to our graph? Increasing. Exponential decay means decreasing. Okay, the next slide it's kind of like a graphical organizer here. There's 4 different ways an exponential function can look. There's only 4 different ways. The first, they talk about when a is greater than 0. These first 2 is when a is greater than 0. Okay, what's a value that we just said we're going to use instead of a? y1. So go ahead and put y1. If y1 is greater than 0, meaning that front value, if your front value is positive, what that means is your graph will be above the x-axis. So scribble this down here away on both of these graphs. If the leading term of your exponential function is positive, greater than 0, your graph will be above the x-axis. I'll say it one more time. If your leading term is positive, the graph will be above the x-axis. Okay? Now, our graphs can be exponential growth or they can be exponential decay. That's based off the base. If your base is greater than 1, the word is, if the base is greater than 1, the word is that the graph diverges away from the x-axis. So in this case, it would make it growth. This becomes growth because if your base is greater than 1, it diverges, that's the word, diverges from the x-axis. Diverge means it moves away from. It runs away from the x-axis. However, if your base was less than 1, and remember, the base has to be a positive number. So that's why it says between 0 and 1. So if your base is less than 1, but still positive, this would mean it converges to the x-axis. So graphically, it would look like this. It would go down and approach the x-axis like an airplane coming to land on the runway. That's kind of the idea. Would you call that growth or decay? Decay, good. Okay, so now let's try these bottom two. This time it's saying A is less than 0. What value will we use instead of A? Y1. If our leading term is less than 0, what do you think that's going to make true for the graph? It's going to be below the x-axis. So go ahead and take away these upper quadrants. Now, if your base is greater than 1, you always diverge away from the x-axis. So that means your graph is going to leave the x-axis and go away from it. So draw your graph like this. As you look at this picture, would you call that growth or decay? Is it increasing or decreasing? Decreasing. Therefore, this is exponential decay. And finally, the last one. If your base is in between 0 and 1, meaning it's less than 1, but of course still positive, it will converge to the x-axis. Since we're coming from underneath, converging to the x-axis makes the graph increase. And therefore, if you're increasing, what do we call it? Growth. So those are the main talking points from lesson 2-3. On the next slide, I have just some questions. Example 1 is basically the questions for lesson 2-3, and then we're going to move into lesson 2-4. I told you lesson 2-3 is one of the quickest they ever had. Okay, so to finish up lesson 2-3 before we get into 2-4, let's make sure you can accomplish what you need to accomplish if I were giving you a test today. From lesson 2-3, what do you need to be able to accomplish? You need to be able to look at an equation, identify if it's exponential growth or decay without using a calculator. So here's how we'd walk through the process. If you had a graph here, you would look at the leading term. What's my leading term in this exponential? 2. And you determine, is 2 greater than 0 or less than 0? If it's greater than 0, the graph cannot be in the lower quadrants. Cool so far? And then you would look at the base, and you determine, does the base converge or diverge from the x-axis? So that was the 2. Now, is my base bigger than 1 or less than 1? 0.6 is less than 1. That means the graph converges to the x-axis. Whoops. Let me try that again. The graph converges to the x-axis. Therefore, would you call that exponential growth or decay? Am I increasing or am I decreasing? This is decay. Let's reload and try again. I know this is called all this together as example 1. I'm going to call it example 2 for lesson 2-3. Tell me about my leading term. 2 is greater than 0. If 2 is greater than 0, what does that mean? It's above the x-axis, so our graph will not be down there. Now tell me about my base. 7/5. It's greater than 1. So what does it mean if it's greater than 1? Does it converge or diverge? Diverges away from the x-axis. So what does that mean then when you put those together? Is that growth or decay? That becomes growth. Because the graph is increasing. All right, I'm going to mix this up a little bit. We're going to make both of these two values negative and negative. Just switch it up. So we get to see a little bit of all four scenarios. So I'm going to make both of those negative. Okay, tell me this time about my leading term. -4/3 is less than 0. What does that mean? The graph will be below the x-axis. And now tell me about 1/6. That's less than 1. 1/6 is less than 1. If it's less than 1, does that mean it converges to the x-axis or diverges away from it? it converges to the x-axis. It approaches the x-axis. So this one now, when you look at it, would this become growth or decay? Is it increasing or decreasing? It's increasing, therefore it is growth. All right, and last one now. Tell me about my leading term, positive or negative? Negative. So if we're negative, then where is the graph going to be located? The lower two quadrants. And my base is 1.3. If your base is greater than 1, what does that mean? If your base is greater than 1? No. Diverge away. This means it goes away from the x-axis. When you look at that, is that graph growing or decaying? Is it increasing or decreasing? Decreasing. Therefore, it is decay. Okay, so that's like basically the first learning thing you need to know from lesson 2-3. The second would be this, just how the equations work. And I have a typo on this one as well. So examine the function f of x equals 3 times 2 to the power of x. Okay, what would 3 be called? Or by symbol. What symbol does 3 represent? The y1 or the a? By symbol, what does 2 represent? Base. This is your initial value. This is your base. What are we doing to the initial value of 3 when the input value is x equals 5? So what we're doing now, we're going to plug in a 5. So if I evaluate f of 5, I need to substitute 5 in for x. So what is 3 times 2 to the 5th power? And here's the typo. This underneath says f of x, and it should say f of 5. Put a 5 there. F of 5 would equal 3 times 2 times 2 times 2 times 2 times 2. Now, where did that come from? Power of 5 means you multiply 2 5 times out. Okay? Now, I want you to think about something because I'm going to lead you into where we're going in lesson 2-4. What if I added one more to the x? So I'm adding to the x. What would happen over here? I would multiply by another 2. What we're going to learn today is if you add another value to the x, you know what's going to happen to the y values? No, not add. You'll multiply. What if I added 2 more numbers to the x? I would multiply twice to the y's. You're going to learn that's going to be the definition of exponentials, is that when x's add or subtract, the y's will multiply or divide. That's what makes something exponential. So if something's linear, you add to the x, you add to the y. If something's quadratic, when you add to the x, you actually add a double amount to the y. It's like you do a second difference. What's true for exponential is that when you add to the x, you multiply the y's. That's what we're going to learn as the day goes on. Okay, so let's go down here and evaluate the last few. I'm going to make sure you can identify the correct pieces. Here's our equation we're trying to identify into that they give us. F of x equals a times b to the power of x. Again, that's what I told you you'll see on delta math. You'll see that all over. According to this model, what would represent the letter A? According to this model. 1.5. Perfect. What would represent the value B? 4. Now, would it be 4 times 4 times 4? Just 4. That's the base. So the x here would be represented by what number? 3. How did you get 3? I don't even see a 3. There's 3/4. So how you would write the equation is this. You'd say f of x equals 1.5 times 4, and you do the power of x, where x equals 3. That's how you would represent it in the form of f of x. Again, if you weren't going to put if you wanted to put a 3 there, you would have to say f of 3. But if you're going to say f of x, you have to put an x there. That was the typo on that part. Okay, let's try it one more time. All right, we got to first evaluate A, then we're going to evaluate B, and then we're going to evaluate X. Or I should say identify. Let's identify our A. Which value do you think is A? 3.2. Perfect. That's our A value. Okay, what about our B? 0.8. And now our X value. You got it. So the equation would look like 3.2 times 0.8 raised to the power of x. Since this says f of x, you'd put an x there, but then you would say where x equals 2. Perfect. All right, let's go look at the College Board questions here. All right, now we're going to begin lesson 2.4. So that right there was all of lesson 2.3. Now we're getting into lesson 2.4. Lesson 2.4 is called exponential function manipulation. And what we're going to see here is there are 5 ways. Technically, it's 3. It's just going to feel like 5. The last 2 properties, I'm about to show you 3 properties here and then 2 rules on the next page. But the 2 rules are actually applications of the properties. So if I wanted to be very technical, I'd say I'm about to show you 3 properties. But for you, I want you to think of it, there's 5 different properties or rules that you need to know to manipulate exponential functions. And here it is. By the way, as I go through, here's the key thing you need to get first today. The rules are hard. It takes some practice to get the rules. Here's what you need to know today. If I ask you, does the property, what's it talking about? I want you to always say the name of the property or whatever the property is doing, it's doing it to the base. That's what I want you to say. It's to the base. So here, when you look at this value, and I say, hey, what's happening? What I don't want you to tell me necessarily is that the powers are adding. What I would rather you tell me is on this side. What is happening on this side of the problem? What is multiplying? The bases are multiplying. If the bases are multiplying, we call that the product property because that's what multiplying means, product. If the bases are multiplying, that's equivalent to powers adding. So some examples. X to the 5th times x to the 3rd. What is actually multiplying here? Your x's. So what is x to the 5th times x to the 3rd? Well, it's the same thing as x to the 5th plus 3. Bases multiplying is the same thing as the, identical bases multiplying is the same thing as the powers adding together. What is the 5 plus 3 going to equal? 8. This is x to the 8th power. That's the product property. Let's do another. 2 to the power of x times 2 to the power of 3. What is actually doing the multiplying? The bases. You have identical bases. So if you have identical bases, you can do the product property, which states, what can I do with my powers? You add them together. Now, finally, this one throws off a lot of students. This is going to be the product property. It just looks weird right now. What can we do to make this similar to these problems up above it? It's the 9. We got to change the 9. What can I do to the 9? 3 squared. What if we made it 3 squared times 3 to the power of x? Now what do I have? Same base, and the bases are multiplying. Which rule can you apply if the bases are multiplying? Product property. And so what do you do with your product property is you write the identical base, and then you add your powers. We usually put x in front, so I'm going to do x plus 2. Just like that. So that's the product property. Okay? Now, a moment ago, I told you that for exponential functions, a definition of them is that as x's add, that's the same thing as multiplying. Y'all remember? Adding x's is like multiplying y's. If you notice here, this multiplication is happening on the outside of the function. That would be a multiplying y, whereas this would be an adding x. So you're going to learn that throughout the day. You're going to see that multiple times. All right, now let's talk about the quotient property. If we said quotient property, what is actually being divided? The bases. I want y'all to be saying the bases, the bases. If I ask, if the question is on the quotient property, what is actually, are we taking the quotient of? What is being divided? You would say the bases, not the powers, but the bases. So if it's a base m divided by base n, that's the same thing as base m minus n as the power. Okay, so x to the 5th minus x cubed, x to the 5th divided by x cubed is equal to x to the 5th power minus 3. And what is that? X squared. And y'all all know that. If you had x to the 5th divided by x3, you could cancel 3 of those x's, and how many are left with? 2. But there it is using the quotient property. Okay, how about 2 to the x divided by 2 cubed? That's 2 raised to the power of x minus 3. Very good. Okay, how about 1/9 times 3 to the power of x? Think about what we did over here. I hear 1/3, but what power did we say? 2. All right, times 3 to the power of x. I'm going to simplify. When you have a fraction and you're multiplying, that means multiply the numerator, divide the denominator. You could rewrite this as 1 times 3 to the x. What is 1 times 3 to the x? 3 to the x over 3 squared. And now I could do the quotient property. 3x divided by 3 squared is 3 to the power of x minus 2. Very good. That's the quotient property. So if adding x's is the same thing as multiplying y's, subtracting x's is the same thing as dividing y's. Because that's the definition of exponentials. Exponentials are proportional. X's add, y's multiply. X's subtract, y's divide. All right, last one. What about if we had a power raised to a power? One base with a power raised to a power. This would be the power property. What you can do is now multiply your bases, multiply your power. So x to the 5th raised to the 3rd. X to the 5 times 3, which is equal to x to the 15th power. Okay, how about 2x cubed? 2x raised to the power of 3. That would be 2 to the power of x times 3, which is the same thing as 2 to the power of 3x. And just like the first two, I try to give you something tricky here for the third example. Here, what could I do with my 9? I could change that to 3 squared times. Here, what could I do with the 3x raised to the squared? 3 to the power of x times 2. And this, you could simplify once and for all. This is the same thing as 3 to the 2x. And what do I do when I have the same bases that are multiplying? Product property, you would add them. So this is 3 to the power of 2x, that's the 2x, plus 2. And like this is saying, I applied 2 different properties. I applied the power and the product that time. That was the power property, and this was the product property. And we got 3 to the power of 2x plus 2. Now, those are the 3 technical properties. Truthfully, everything can be summarized in those 3 properties, but there are a few examples that students get confused and forget how to apply the properties, so I just threw them in as 2 different rules. Truthfully, these are application of these properties. I'm going to call this the fractional exponent rule and the negative exponent rule. So I'm going to add in the word rule here, because truthfully, these aren't properties. It's just an application of the property. And so here's the symbols for you. One thing I want to add to this so you know, when you have a power that's a fraction, so the base raised to a power that's a fraction, you can change it to a root. The denominator becomes the type of root, whether it's the second root, third root, fourth root, whatever. And the power c, this power c can go on the inside or the outside. Mathematically, it's the same. So I want to rewrite this a second time. And I want you to put the power of c on the outside of the root. Different times today, we're going to use it either way. Over here, I don't want to forget, I'm going to do the same thing. When you have a negative power, that's the same thing as taking the reciprocal of the base. And that's what I've done here. I've sent this base that wasn't a numerator. I've set it to the denominator. You could also rewrite it like this. 1 over base raised to the power of n. Notice I took away the negative power when you take the reciprocal of your base. So here are some examples just to show you what this is. X to the 3/4 could be rewritten as the 4th root of x cubed, which you could also write as the 4th root of x all cubed. Both are mathematically equal to one another. That's what you can do with the fraction power. 4 to the 1/2. Let's see if you have figured out how you can rewrite this. 4 to the 1/2, I can rewrite this as a root. It's a second root, which is the same thing as a square root. So I could rewrite this if you desired with the 1 on the inside or the outside. If it's a square root or a second root, you do not have to put the symbol there. A second root is a square root. You don't have to keep the 2 there, nor do you have to keep a 1 there. What is 4 to the first? 4. You can just do it like that. And what is the square root of 4? 2. There you go. That would be applying the fractional exponent rule right there. That 4 to the 1/2 is 2. That just means the square root. All right, last one. 9 to the power of x over 2. I could rewrite that as a root. It's a fractional exponent. By rule, we could change it to a root. What type of root is it? If it's x to the x over 2 power. It's a second root or a square root. I could put that x on the inside, or I could put it on the outside. I'll do it first on the inside. Now I'm going to rewrite this, and I'll put it, I'm not going to write the 2 this time. Why do I not write the 2? Square root, do you need to write the 2? No. I'm going to put it on the outside this time. The power of x on the outside. And the reason I did that is because we know what the square root of 9 is. What is the square root of 9? 3. And you could rewrite this as 3 to the power of x. What I am doing on all these examples you're watching me is I'm manipulating an exponential expression. That's what we're going to spend today doing. That, and we talk about what type of transformation it is. Okay, last time around, a negative exponent. What a negative exponent is to get rid of a negative exponent, you take the reciprocal of the base. So this says x to the negative third. The way I would, if I were you, I would write it immediately is I would write it as 1 over x. You take the reciprocal of the base. Reciprocal means flip. Doesn't mean opposite. It means flip. So since it's x, it's kind of like x over 1. You make it 1 over x, and now the power becomes positive. That's how I do it first. And if you wanted to simplify, now you could think about what 1 cubed is and x cubed. What is 1 times 1 times 1? 1. And what is x times x times x? X cubed. And you could write it that way if you desire. Both of these are the same. Okay, let's try it again. 2 raised to the power of negative x. How can I rewrite that? How do I get rid of a negative power? Reciprocal of the base. What's the reciprocal of 2? So 1 over 2 to the power of x. And if you wanted to, that's 1/2. We don't know how many powers of it, but what's 1 to the power of x going to always be? What's 1 to any power? 1. You could leave that as a 1, and then 2 to the power of x. All right, last one. This one should have a parenthesis. That's a typo on my part. That needs to have a parenthesis there. If it's a fractional base, you need to have a parenthesis. Okay, what's 1/4 to the power of negative x going to be equal to? 4 over 1 to the power of x. And you can rewrite that as 4 to the x. What's 1 over x? 1. And when you divide by 1, it's still going to be 4 to the power of x. There it is. There's all your rules and properties. So the rest of the lesson, what I'm going to do is we're going to roll through the math of just applying these. I think I'm going to walk through maybe 12 examples or so. That's what I'm going to do. What we're going to see is that these properties will produce equal equations, but they look quite different. So on the next slide, I've given you the next 2 slides, 2 pictures to show you this. Here's the original function. In red is the transformed. Tell me about this red in the middle section versus this red on the far right section. How do the reds look compared to one another? They look the same. But look at their equations. Are the equations the same? No. What I want you to mark down on this one is notice that I am adding x's here. Now, I know x's are a liar. Don't get caught up with that. Just I'm adding 2x. That produced a graph that was Now over here, I'm not adding to the x, this is the y. Am I adding 8 to the y's? What's that 8 doing? I am multiplying on the outside, which means I am multiplying the y's. That is the definition of an exponential function. Let's say it one more time. An exponential function is proportional. That's the word you got to know. Off the desk here. You need to know that exponential is proportional. What does that mean? Your x's add, what happens to the y's? They multiply. That's the way the function works. If you add to the x, you multiply to the y. It makes sense? Whether or not, that's the definition of an exponential. That's what it'll do. Adding x's will multiply the y. Subtracting x would divide the y. Okay, next slide. Once again, compare the red to the red. What do you notice about the reds? They're the same. Look at the equation. Are the equations the same? No. We can manipulate an exponential function to where we get the same graph, but with a different equation. And we do that by applying rules. This time, what's that 3 doing to the x? Okay, if you multiply the x, what does that do to the y? Actually, it doesn't do the y at all. It changes the base. That's all it does, is it changes the base, which is the note right below it, but I'm going to say it again. Changes the base. So the definition of exponential is not multiply the x, change the base of y. That's not the definition. The definition is of exponential is that it's proportional. Adding x's, multiply the y's. But if you wanted to multiply the if you wanted to multiply the x's, that changes the base. That's what it does. Okay, I've given you a million different rules. Let's start going methodically through this, and I'll let you see them a bunch of times for this lesson 2-4. Let's take a look at what I'm going to call example 2. This is the first example for lesson 2-4. All right, this one, it starts real basic. I'm going to add to the instructions here. It says, determine the transformations of the following exponential functions. And you would need to know where you're starting from. So on this one, let's say we were starting from the equation y equals 4 to the power of x. As you compare example A to what I just wrote up above, what do you notice is different? We're adding to the x. So I'm going to have 3 questions for you today. The first thing I'm going to ask you is the math that's changed, is it a horizontal or a vertical transformation? Meaning, am I affecting the inside x values or the outside y's? Here, this +2, what am I changing? The x values or the y values? The x. So is it vertical or horizontal? Horizontal. That's the first thing we're going to do with transformations. It'll be 3 questions. 1, is it horizontal or vertical? Meaning, am I changing x's or am I changing y's? Second question is, what type of transformation is occurring? What type of transformation is occurring? Is it here's your 3 options, a translation, a dilation, or a reflection? Dami Solo. Off your desk. What is it? A translation, dilation, or a reflection? If you add, which of those is it? Translation. It's a horizontal translation. That's the second question, is what type? Translation, dilation, reflection. And the third is this. Is it a liar or truth teller? When it's with an x or a horizontal, is that a liar or truth teller? A liar. So show me an x-axis with your arm. If you subtract the 2, which way do you move on that x-axis? If you subtract the 2, I'm hearing people say right. If you subtract 2, you actually go left. If you subtract 2, you go left. I want you to put left 2. Oh, y'all answered the question, but I think you forgot. I asked, is x a liar or a truth teller? Liar. So when it says +2, what actually happens graphically? You subtract 2, you go the opposite way, to the left 2, because it's a liar. Okay, now that's determining the transformation. That actually is all it asks us to do, but that's not what you're going to be doing on your homework, so I'm going to practice it here with you. Here's what we're going to do. We're going to apply the properties. Right now, I have a power that's adding, but that's not any of the rules I gave you. Remember, the properties were product, quotient, and power rule. When you have powers that's adding, you need to think about the base. What would be happening to the bases if your powers are adding? Multiplying bases. Let's rewrite this as 4 to the power of x times 4 squared. That right there, in case you want to look at it later, is called the product property. That's the product property. Okay, now what we'll do after we apply the property is we will simplify anything that does not have an x. So 4 to the power of x I cannot simplify, but I can simplify 4 squared. What is 4 squared? 16. So here's how we're going to write the final version of this equation is 16 times 4 to the power of x. 16 has become the initial value. 4 is your base. Power is x. To finish it up, let's identify this transformation so you can, again, we're going to compare this to that. The transformation that's now occurring is this 16. Is this 16 inside with x or on the outside, meaning it's a y? Outside. So what's the word for y's? Is it horizontal or is it vertical? Vertical. That's the first thing. It's on the outside, therefore it's vertical. That's the first question for transformation. Second, when you're multiplying, does that make it a translation, dilation, or a reflection? It's a dilation. Now, if it's a translation, you say the direction. If it's a dilation, you always say by factor, and then you put the value. Is 16 a truth teller or a liar? Truth teller. So it's by factor 16. Notice. This is why I'm going to do this so many times today. This is what you have to get down. For an exponential function, if it's a horizontal translation, that means the x's are adding. What will it be in the very end? Vertical dilation. Why is that the case? Because by definition, exponentials are proportional. What does that mean? X's add, y's multiply. X's adding is the same thing as a y multiplying. And that would be true with subtraction and division. But that's what you have to get down, is that exponentials are proportional. Are you getting the word proportional, what that means? What does proportional mean? X's add, y's multiply. And that's how your transformation is going to work. This is going to be tested over and over and over throughout the year. So that's why I keep saying it's critical you get this down. All right, this next time. Let's compare part B to the equation y equals 2 to the power of x. If you compare these two, what transformation has occurred this time? What value do you see has occurred this time? Okay, I hear the x is multiplying. So if it's the x, what word do we use? Horizontal or vertical? That's the first question. Horizontal. If it's multiplying, what's the name? Is it a translation, dilation, reflection? Dilation. With a dilation, you always say by factor. Now, next question. Is it a liar or a truth teller? Liar. So do I put a 3 that's multiplying? You put a dividing of 3, which is like a fraction. Therefore, you got to put a 1 as a placeholder. So it's a horizontal dilation by factor 1/3. Now, this one's weird. This one doesn't fall under the definition of an exponential. Remember, the definition is proportional. X is add, y is multiply. What am I doing this time, though? X is multiplying. So this is going to be something different. It's not going to be that true definition. Okay, what could I do with the power that's multiplying? Do y'all remember? A power that's multiplying is the same thing as a base raised to 1 power raised to another power. Remember, you always talk about the base. A base raised to 1 power raised to the next power, like that. You could write it that way. That right there is called the power property. That's what I just did. That's the power property. To finally simplify it out here, you simplify anything that doesn't have an x. Does 2 cubed have an x? No, you can simplify that. What is 2 cubed? What is 2 times 2 times 2? 8. So this is 8 to the power of x. This time, I would not say anything about the vertical because this is not the definition of exponential. Remember, exponential is proportional. This isn't part of proportional, horizontal dilation. So what has happened here? Tell me about my base. What has happened to my base? There it is, and that's the name. It's a change of base. The base was a 2. Now my base is an 8. Any questions on this one? All right, I'm going to show you more. Yep. All right. Let's look at part C. Now this right here, let's compare it to y equals 9 to the power of x. If I compared this to y equals 9 to the power of x, what transformation do you see has occurred? What's different in the equation they gave us? My x is being divided by 2. If my x is being divided by 2, is that horizontal or vertical? First question. That's horizontal. Second question, if you're dividing, is that a translation, dilation, or a reflection? Dilation. If it's a dilation, you always say by factor. Now, is it a truth teller or a liar? A liar. So I don't have to do 1/2. I do the reciprocal of 1/2, which is 2. You just put a 2. You don't have to have the 1 there, just a 2. Okay, different question. Is this going to be falling under the definition of an exponential? No, because this is saying x's are multiplying. So it's not going to be changing the y. It's going to do something different. Did that give you a hint? Why is it not changing the y? Because it's a horizontal multiplication. It's a different transformation. It's not going to change the y. It's going to do something different. All right. Does anybody remember what you can do with a fraction exponent? You can change it to a root. What type of root are we doing this time? An x root or a square root? Or a second root, I should say. A second root or an x root? Answer is second root. Okay, you can put the x on the inside or the outside, doesn't matter. This is the fraction exponent rule. Fraction exponent rule. And you could do it, like I said, you could put the x on the inside or you could put the x on the outside. I dropped the 2. Is that a mistake? Do you have to have the 2 there? Nope, you don't. Okay, so what can we do next? What you always do. You evaluate anything that does not have an x. How about square root 9? So this becomes 3 to the power of x. To finish this off, this did not fall under, so we're not going to talk about vertical here. What happened then? Change of base. You got it. Change of base. What was the original base? 9. What did it become? 3. We manipulated the equation. That's why this lesson 2.4 is called exponential function manipulation. We are manipulating ours. All right. How about you go to the back of the packet, try College Board number 5 problem here. Try number 5. Example 3. From here on out, we're going to say, or on this example, let f of x equal 3 of x. Let g of x be the transformation of f. For each problem, name the transformation. We're not only going to name the transformation, we're also going to apply our properties just for good practice, okay? On this one, what transformation has occurred from f of x to g of x here? What has changed? What do you see has changed from f of x being 3 to the power of x to g of x 9 times 3 to the power of x? This right here. That's the only thing that's changed. Is that inside affecting the x's, or is that outside affecting the y's? Outside. So what's the word for that? Vertical. Mathematically, what's happening? Adding, subtracting, multiplying, dividing. What operation has occurred? Multiplying. If I'm multiplying, that's called a dilation. Anytime you do a dilation, it's by factor. Is this a liar or truth teller? Truth. So it's just by factor 9. Okay, question. Will this fall under the exponential definition? A vertical multiplication? Yes. So what should we get at the end? On adding of x's. Let's see what happens. Okay, if you were going to simplify this, the first thing I would do is I would break down 9 into factors of the base. What is 9 in terms of the base of 3? 3 squared. Let's rewrite that as 3 squared times 3 to the power of x. That was just a little algebra there. There's no special name for that. But there is a name for the next one. What happens when you have the same base multiplying? Product property. What can I do with the product property? You add your exponent. So this right there was the product property. That's the product property. Okay, now we're done. But let's rename this transformation. So comparing 3 to the power of x, f of x equation with the g of x's equation in this form, 3 to the power of x plus 2. The x plus 2 is what's changed, the plus 2. Is that a horizontal or vertical transformation now? It's horizontal. When you are adding, is that a translation, dilation, or a reflection? That's a translation. And when it's a translation, you always say this direction. It says x plus 2. Is that a liar or truth teller? Liar. So on the x-axis, show me an x-axis with your arm. You go -2. Which direction is that? To the left 2 units. All right. Let's reload and try again. Part B. What transformation has occurred this time? When you compare f of x to g of x, the new g of x. It's being divided by 27. Now, is that division of 27 only dividing the x, or is it dividing the whole equation, meaning the y's? It's dividing everything. So if it's dividing the y's, is it vertical or horizontal? That's a vertical. Dividing, is that translate, dilate, reflect? Dilation, that's right. Dilation. With a dilation, you always say by factor. Last question for you here. Is it a liar or truth teller when you're dealing with vertical transformations? Truth teller. Dividing by 27, the way you represent that is a fraction. With this 27, the denominator, you put 1 in the numerator as a placeholder. Okay, just like before, we're going to rewrite this into a different form, just for good practice. So let's rewrite 27 in terms of a base of 3. How could I rewrite 27 in terms of a base of 3? 3 cubed is 27. 3 times 3 times 3 is 27. Now, that is a property. When you have identical bases being divided, what property can you use? Quotient property. Good. Do you remember what happens? We subtract. That is the quotient property right there. That's the quotient property. If I wanted to name this transformation, tell me about the location. Is that a horizontal location or a vertical location for that transformation? That's horizontal. Good. When you subtract, are you translating, dilating, reflecting? Translation. And with translations, you always say the direction. So if you show me an x-axis, is it a liar or a true teller? A liar. So it won't be -3, it'll be +3. If you go +3, You move to the right 3 units. Notice this is also a definition of an exponential. If you were to, that the y's were to divide, that means the x's are to subtract. If the y's divide, the x's subtract. Okay? Go to the back of the packet, try number 1 now. Example 4. And we could read the instructions. It says each of these have some type of horizontal translation. For each, write an equivalent representation that has a vertical dilation, no horizontal translation. But I'm going to do this as I've been doing it before. If the parent function was y equals 2 to the power of x, what has changed in this example here? I'm adding 3. Am I adding 3 to the x or the y? X. Does that mean it's horizontal or vertical? So this is a horizontal translation because translations add or subtract. And with translations, you say the directions. Now, is x a liar or a truth teller? Liar. So it actually moves left 3 units. Okay, good. Now, let's apply the math. A horizontal translation is going to become, by definition, this is proportional, a vertical dilation. And we're going to multiply y. So let's see what happens. If you remember, adding of powers is the same thing as doing what to your bases? Multiplying. So it becomes 2 to the x times 2 cubed. That right there, that property was called the product property. That's what that is, the product property there. Okay, now 2 cubed is what value when you evaluate that? So you simplify anything that doesn't have an x. That's what you do from this step. 2 cubed is 8. I'll put that in the front as the initial value. So it's 8 times 2 to the power of x. Now tell me about this 8 in terms of transformations. Is that vertical or horizontal? Is this inside or outside? Outside. So it's vertical. When you multiply, what type of transformation is that? A dilation. And dilations always say by factor. Is it a liar or a truth teller? It's vertical. Truth teller, so it's by factor 8. Okay, I'm going to do one more here. This, if you were comparing to y equals 3 to the power of x, this has 2 transformations this time. Tell me about the 4. Vertical or horizontal? This is vertical because it's on the outside. It's multiplying. What does that mean? Dilation. And dilations always say by factor, and you're telling me that's the truth, and I agree with you, so you just put it as a 4. Okay, we have a second transformation though. Inside or outside? No, it's inside. So it is horizontal. It's adding, so that means it's a translation. And since it's a translation, you tell it which direction. X goes to -2, which means left 2 units. All right, if you wanted to mathematically manipulate this equation, what you would do is this power right here. We would need to do this horizontal translation. That's what it asks us to do anyways. So what I can do with a power that's adding, if you think of the base, I can do something to my base. Do you remember what it is? When a power adds, you can make your bases multiply like this. My bases multiply. That right there is the power property. Now I'll go to simplify. I will have a 4 times a 3 to the power of x times what's 3 squared? Times a 9. And I would actually just rewrite this one more time. The 4 can multiply with the 9. What's 4 times 9? 36. So this would be 36 times 3 to the power of x. That 36, is that inside or outside transformation when you compare it to this? Outside. So that's a vertical. When you multiply, what are we doing? Dilation by factor 36. And now we could try deal with number 3 and 6. All right, example 5. So it says let f of x be 3 to the power of x, let g of x be the transformation of f. For each problem, name the transformation of f. Well, right now, we don't have a transformation, but I can see I have a different base. So how I would solve this is I would need to change the base. So if this is a different base, again, what I would do is I would write it as 3 squared to the power of x. Now, all I'm doing there is performing a little algebra. I'm changing the base. That's all I've done here, is I've changed the base. Now, if I'm changing the base, this will not follow the exponential definition. It won't be a horizontal translation here. It won't be an adding of x's, but this would rather be multiplying. So you can multiply those two together there, and I would say this is 3 to the power of 2x. So 3 to the power of 2x, that does have a transformation from 3 to the power of x. I am multiplying by that 2, and that 2 is on the inside, therefore it is horizontal. And whenever you multiply, that is a dilation. And with dilations, you always say by factor. Goodness. By factor. And since this is an x or a horizontal, it's a liar. So instead of multiplying by 2, what I actually do instead is I'm going to multiply all the x values by 1/2. All right. And finally, what about this one? This one's made to look a little weird. So I have g of x equals f of x raised to the power of -3. Let's substitute in. What is f of x? Well, f of x that we're substituting in here is 3 to the power of x. And then we're going to raise this to the power of -3. Well, that right there is the product property. You know what? I forgot to write that over here. That is the, not product property, that is the power property. I forgot to write that right here. This is the power property. Okay, and so now I'm going to apply that same power property this time. I'm going to change this to 3 to the power of a -3x. That right there is the power property. Now there's a few things we can do here. One, I could stop and state transformations because I do have a 3 raised to the power of 1/3. Actually, for this one, I should stop here because I have the correct base and I have it just with the transformation. So this is technically 2 transformations. I want to make sure you see there are 2 transformations here. I have a transformation in the negative. So this is a horizontal reflection. Horizontal because it's on the inside of the x. It's a horizontal reflection. And if it's a reflection, you need to state what x-axis it goes over. Which x-axis. If it's a horizontal, that means you're reflecting left and right. So I want you to think about this. If you reflect left and right, you cross over the y-axis. And so we would say this is a horizontal reflection in the y-axis. I know it's weird. You think of a cross, but it's truthfully in the y-axis. It's a horizontal reflection in the y-axis. Okay, that's one transformation. And we have a second here, is I'm also multiplying by 3. So this would be a horizontal dilation. And if it's a dilation, you always say by factor. Since it's a horizontal, it's going to be a liar. Instead of multiplying by 3, we would divide by 3. Therefore, it's 1/3. All right, so now you can go try number 4 at the back. And now our final example of the day, example 6. Let's evaluate some function given some input value. So this time we're just going to evaluate. If I wanted to evaluate h of 1 here, I would need to substitute a 1 anywhere. I have an x, so this would become the initial value of 2 times the base of 5 raised to the power of 1/2. I want to write it this way, parentheses, so you can see better what's going on. Now, if you remember, this is the fraction. This is going to be the fraction rule. And so let me go ahead and write that out. This will be the fraction exponent rule. Fraction exponent rule. Which means this. You could rewrite this as 2 times, and you change it to a radical or a root. The 2 goes here. The 1 goes either inside or out. Doesn't matter. I'll put it inside. Just like that. Now, because of this algebra, I can reduce using algebra here. This would become 2 times, this is just the square root. You don't have to have the 2 of 5, which we don't have a square root of 5. So I'll just say over here, h of 1 equals 2 square roots of 5. And I'll leave that as my answer there. That's how you would evaluate that exponential equation at 1. All right, now the second exponential equation here, if I want to evaluate this at -2, I would say h of -2 equals 6 times 2 raised to the power of, and again, I'll do parentheses here, the -2/3. Well, applying some of our properties that we know here, what I could do first off is I'm going to apply that the negative exponent rule, which means I can change my base and take the reciprocal of the base, so it's now 1/2 to the power of 2/3. And now I will apply the fraction rule, the fraction exponent rule. I'll now do that. And so with the fraction exponent rule, we change the fraction power to a root. So this will be 6 times the third, it becomes a third root, and it'll be 1/2 squared. Again, you could put the squared on the inside or the outside. I'll leave it on the inside, and I'm going to evaluate it. So I'll go ahead and put this in parentheses to the 1/2 squared. So I can evaluate that. This will be 6 times the third root, and 1/2 times 1/2 would become 1/4. And if this were a square root, we could simplify that, but it's not, it's a third root. So I don't know how that simplifies, so I'm going to have to leave it as h of -2 equals 6 times the third root of 1/4. You know what we could do if you wanted to? We could simplify the third root of 1. You know, I could do it like this. 6 times 1. You know what? I'm not ready to write the final answer. I'm going to show you how I can do this. That is equal right here to 6 times 1 over the third root of 4. And I could simplify 6 times 1. And so now I'll rewrite it as h of -2 equals 6 times the 1 is 6 over the third root of 4. And I could write the answer in that form. All right, with that, you can try number 2 at the back of the packet. And once you do that, you can submit your answers. You can submit your answers by going here.